Okay, let's go ahead and get started with section 2.2. In this section, we are just going to do 3 examples in which we do a complete hypothesis test from start to finish. Okay, let's go ahead and get started. The first example that we're going to look at in this section is the gender discrimination example that we've talked about previously. The research question for the gender discrimination case was again, is there evidence of discrimination against females for those chosen for a management position within this company? The parameter value that we specified was the probability of a female being selected for a managerial position. That probability would be equal to 60% under a fair situation or a situation of no discrimination. So that is why the parameter value is set to 60% under the null hypothesis. The null hypothesis again represents how the simulation model is being set up. The alternative hypothesis is the hypothesis that supports the research question. In particular, we were interested in whether or not females were being discriminated against. And if that's the case, the probability of a female being selected would be less than 60%. So the alternative hypothesis represents the research question. This is indeed a left-tailed analysis, because if there were too few females selected for a managerial position, then that would be discrimination against females. We care about the left edge of this distribution. The observed outcome from the study is 9. There were 9 women selected out of the 20 that were being investigated here. Before determining the p-value, we need to determine what values are as extreme or more extreme than the observed outcome. When doing this, we need to concern ourselves with which values support the research question or provide additional support for the research question. So here, values as extreme or more extreme than the observed outcome would be 9, that's as extreme, and then even more extreme would be lower values. So 8, 7, 6, 5, 4, 3, 2, 1, and 0. So in determining the p-value, we need to concern ourselves with values 9 and below, and that is what is done on the reference distribution app. When using the reference distribution app, we specify the probability of success for this problem to be 0.60, that's 60%. The number of trials or the sample size for this example was 20, and the number of repeated samples here, the repeated outcomes that I'm going to obtain through my simulation model, I set that to be fairly high at 5,000. Down in the lower left-hand corner, I can specify values as extreme as. Here I want to enter the study outcome of 9. When I do that, the app will automatically determine how many observations, of the 5,000 that is, how many of those observations from my simulation model sit at 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. And when that is done, there are, I guess, 625 observations that are as extreme or more extreme than my study outcome of 9. That is 625 out of 5,000. That ratio turns out to be 0.125. Therefore, the p-value for this analysis is 12.5%. So let's go ahead and identify that here. So the p-value is going to be 625 divided by 5,000, which is 0.125 or 12.5%. Again, the 625 here, there are 625 dots as extreme or more extreme than the study outcome. That's where that 625 is coming from. How about our decision rule then? We call the decision rule is if the p-value is less than 0.05, then the data is said to provide enough evidence for the research question. So we must ask ourselves here, is 0.125, which is the p-value that I computed up above, less than 0.05? And the answer here is no, it's not. Therefore, in this particular example, we do not have enough evidence for the research question. Let's go ahead and write a conclusion in layman's terms here. Recall that the conclusion has three components. The decision, so that there is going to be what? The data does not provide enough evidence here. So that's going to be the decision. That's the first component there. The data does not provide enough evidence. The second component then is simply going to be a restatement of the research question, which let me just go up here, copy and paste that down. The research question here was asking about enough evidence of discrimination. So if you have a research question that's carefully written out, we can use that right in our conclusion. So let's see how this reads so far. The data does not provide enough evidence of discrimination against females for those chosen for a management position within this company. Providing an answer to that. We don't need the question mark then. The only other component that we like to include on a conclusion is the actual p-value. So let's go ahead and put that in there. The p-value is 0.125 for this example. And those are the three components of a conclusion. If you have those three components of the conclusion, the conclusion is complete, excuse me. Let's just read that all the way through. The data does not provide enough evidence of discrimination against females for those chosen for a managerial position within this company. The p-value reported here is 0.125. All right, let's move on to our next example. Our next example is going to be a new example, and this is going to be the helper-hinderer case study. In this study, there were infants that were presented one of two outcomes. Okay, so a little bit of a framework for that. Let's go down here to the next page. The two outcomes that the infants were presented with were either the helper toy or the hinderer toy. This little red circle here was trying to get up this little hill. The helper toy would come down below this red circle and try to push it up the hill, so help the toy up the hill. And therefore, this toy here, which is a gray square, is identified as the helper toy. On the other hand, there was something called a hinderer toy, and the hinderer toy would come down from the top side and would try to push the red circle down the hill. Wouldn't allow it to go up to the top. We called that the hinderer toy. These two toys, the helper toy and the hinderer toy, were presented to 10-month-old infants, as is shown here on this table. This particular child ended up picking the gray, helper toy. So the one here on this child's right-hand side. What they did is they just identified which toy the child went to first. So if the child leaned and touched the helper toy first, then they indicated that that child would prefer the helper toy over the hinderer toy. There is a short video for this study that has been provided on our course website. If you want to take a moment now and go watch that video, please do. Okay, I hope that video filled in some of the details about how this study was conducted. Let us consider the following schematic for this investigation. There were a total of 16 10-month-old infants that participated in this study. 14 of those infants picked the helper toy over the hinderer toy. So the study outcome here would be 14. If all of the children preferred the helper toy, okay, so let's suppose that 16 out of the 16 children picked the helper toy, that's going to suggest preference for that toy. On the other hand, if none of the children picked the helper toy, okay, so if none of the 16 actually picked the helper toy, they would have preference towards the hinderer toy. So down here on the left-hand side would be preference for the hindering toy, and the right-hand side here would be preference for the helper toy. Now, if children had no preference at all, okay, they're going to be in the middle of this number line. All right, so if children really didn't care whether or not it was the helper toy or the hinder toy, they just went ahead and picked a toy, then we'd expect that outcome to be near the middle. In this particular study, there were two possible outcomes, either the helper toy or the hinder toy. There were 16 trials. The expected number would be 8. We would expect 8 to pick the helper toy under a situation of no preference. Parameter value is 50%, two choices. Under no preference, they're equally likely to pick either choice. Okay, I think we discussed each of the elements of that schematic, so we can move on. What is the research question here? The research question was, do 10-month-old infants prefer the helper toy over the hinderer toy? The null and alternative hypothesis are stated here. The parameter for this particular example is going to be the probability that a 10-month-old infant is going to select the helper toy. Again, if there's no preference, then I would anticipate that parameter value to be set at 50%. And that's how the null hypothesis is set up. The alternative hypothesis is, again, aligns itself with the research question. The research question here is asking about preference towards the helper toy. So if that is the case, then that parameter value, the probability of a 10-month-old selecting the helper toy, we'd anticipate that to be greater than 50%. We'd expect that chance and that probability to be greater than a 50-50 scenario. We care about the right edge of this distribution. Let's go back up and look at our schematic again. The right edge of this distribution is indicating preference towards the helper toy, and that's indeed what the research question is being asked here. So what values are as extreme or more extreme than the observed outcome? That would provide even additional evidence for the research question. Well, here that's going to be 14, 15, and 16. So these values here provide these values here, are as extreme or even more extreme that provide evidence for the research question. So when computing the probability, or the p-value, we need to add up the proportion of dots that are at 14, 15, and 16. And again, the reference distribution app does that for us. This reference distribution app here was done with 1,000 repeated simulation outcomes. The parameter value is being specified as 50%. The number of tosses, or the number of trials, is 16 here. In the as extreme as box, we're going to select 14 here. Again, that's the study outcome. And this time I only had 2 dots that were as extreme or more extreme than the study outcome. So what that means is that 14 is a pretty unusual outcome against this reference distribution. This reference distribution again represents the situation of no preference. And 14 is an outlier against that reference distribution. And in fact, it's an outlier on the upper side. It certainly meets the 5% threshold. And if it's an outlier on the upper side, that's going to indicate preference towards the helper toy. So again, what is the p-value here? The p-value is computed by 2 divided by 1,000. So in this particular case, I used 1,000 simulated outcomes, which is 0.002. Again, what does this represent? Or if I were to ask for an interpretation of this value, there is a 0.002 likelihood that we'd observe, that one would observe 14 or more picking the helper toy under a situation. So again, this is under the situation of no preference. So as I've stated here, this certainly suggests, this is an outlier, so this certainly suggests that children probably do have a preference. So even at a young age of 10 months old, these infants are able to separate the difference between a helper toy and a hinderer toy. Okay, how about the decision rule here? Again, we just need to ask ourselves if this probability is less than 0.05, and it is in this case. So is 0.002 less than 0.05? The answer to that is yes. So let's go ahead and make our decision here. So the data does provide enough support for the research question. All right, let's go ahead and write our conclusion again in layman's terms here. So we'll start with the decision. So the data does provide enough evidence. That's the first part. I need the research question next to say that 10-month-old infants have a preference for the helper toy. The p-value for that statement is quite small at 0.002. All right, we have the three components of a conclusion. Again, those components are the data does provide enough evidence. It's a decision to say that 10-month-old infants have a preference over the helper toy. It's going to be the research question, a restatement of the research question. And then the probability value is also provided. All right, let's go ahead and talk about a couple of comments regarding this example. The first comment here on page 6 is just talking about the fact that the number of repeated simulated outcomes should not adversely affect the calculation of the p-value. Certainly the p-value is going to change slightly if I get a different number of dots, but it shouldn't change too much. In our example, I obtained 1,000 outcomes. Okay, so I obtained 1,000 repeated simulation outcomes here, two of which were as extreme or more extreme than 14. If I were to jack this number of repetitions, the number of repeated simulation outcomes, up to 10,000, I would hope that this probability value wouldn't change very much. Certainly I'm going to have more dots out here on the edges, but I also have a lot more dots in the middle as well. So what happens if I were to increase the number of simulated outcomes to 10,000? That's what's shown here in the middle of page 6. When that was done, we can see that the probability value changes slightly. In the situation with 1,000, I had a probability value or a p-value of 0.002. Here, when I use 10,000, the p-value changed just slightly to 0.0022. Okay, so that again provides some comfort in knowing that the p-value is not going to change a whole lot whether or not you use 1,000 repeated simulated outcomes or 10,000 repeated simulated outcomes. Now that is true given that you're using a sufficiently large number to begin with. If I were to compute a reference distribution with, let's say, only 50 repeated outcomes, then what I'm saying is not going to be true. You need a sufficiently large number of repeated outcomes on your reference distributions in order to be certain of what that p-value estimate is going to be. Commonly, anything, say 1,000 or bigger, is usually what is used. You can certainly use more. Let us consider another important aspect of this study that we have not talked about up to this point. Near the end of the description of this study, there's a statement that's made. The color, shape, and order, left side or right side, of the toys were varied and balanced out among the 16 infants. Now, why would they do something like that? What is the implication of that statement? Suppose that all the children received exactly the same setup for the experiment. In particular, suppose that all children were presented the situation in which the helper toy was always the gray square and presented on the right-hand side of the tray, and the hinderer toy was the yellow triangle, always presented on the left-hand side of the tray. Now let us suppose that 14 infants picked the helper toy like we had in our study. An important concern here presents itself. In particular, one cannot be certain that these infants picked the helper toy because it was a helper toy. Maybe it was because the kids don't like yellow, or maybe the kids don't like triangles, or maybe they just tend to pick the toys that are on the right-hand side because most of us are right-handed. The statement that the color, shape, and order of the toys were varied and balanced out for the 16 infants suggests that these factors were taken into consideration when designing the study. And in particular, they did this in order to prevent these variables from being confounding variables. Okay, so we've talked about confounding variables before. Those are variables that just kind of muddle what we're trying to say in our conclusion. Okay, we can't be certain it's because of the variable that's being studied. Maybe it's because of some other variables. We considered confounding variables in the breastfed bottle-fed example in the previous section, in section 1.4. In section 1.4, in that case study, we talked about the matched paired process that was used. In other words, they tried to identify variables that were important to ear infection, and then they matched on those variables. In this particular study, they did that to prevent confounding. Here, we have to do the opposite effect in this particular experiment. We want to vary the setup as much as possible for each of the children. In doing that, we will actually prevent confounding. So there's not a systematic way there's not a systematic way to determine how confounding must be adjusted in a particular study. Each study must be considered carefully in order to prevent these types of variables from influencing or adversely affecting our study outcomes. Okay, let us consider the third example presented in section 2.2. This is a new example, and it's the WSU vitamin case study. This is a case study that I was actually involved with, and it was done by a couple of biology majors for their capstone project. The goal of the study was to investigate the intake of various vitamins for WSU college students. A total of 71 WSU students participated in this study. 57 of those were women and 14 of those were men. The intake of all food was carefully measured over several days. The researchers then evaluated the types of food that they ate and the exact amount of food that they ate. And from this computed an average daily intake for energy, vitamin A, vitamin C, calcium, and iron. For the analysis here, we will consider vitamin A. This data is provided on the course website, and it is in a spreadsheet format as shown here. Now, in order to utilize the two alternative choice models that we've been working with, we need to compute a count of one of the two possible outcomes. And what we're going to do here is just determine whether or not an individual was above or over their daily recommended intake of vitamin A, or was an individual under their daily recommended intake for vitamin A? So the two outcomes here are going to be either over or under their daily recommended intake. Okay, so here we can see in this picture of the spreadsheet, we actually have their actual amount of vitamin A taken, and then we have their DRI value, which is their daily recommended intake. For these first few people, we can see that the actual amount of vitamin A was above their DRI value. But here, the fifth person, ID number 5 here, we can see that their vitamin A intake was actually quite low. It was only at 164 when their DRI value should have been 700. We can use a spreadsheet function to easily compute whether or not we were over or under. And that spreadsheet function is a simple if statement. So what I'm doing here with this if statement is just determining whether or not the contents of cell H2 is bigger than the contents of cell I2. In this case, it is. If that condition is true, then we're going to identify or label that row or person as over. If that's not true, we're going to identify that person as being under their daily recommended intake. So this simple statement here will allow us to real quickly go through all the people in our study and identify whether or not they were over or under their daily recommended intake. Next, we need to tally up or count how many unders and overs we had. Okay, and here I'm going to use the COUNTIF statement to accomplish this. So a COUNTIF statement will look over a set of cells and will create a tally for cells that match a certain condition. Now I ended up providing these counts for males and females separately. And this is what we did in the study as well. In the analysis for the study, we considered females and males separately. So how many females were over their vitamin A intake? In order to compute that, we simply use the COUNTIF statement. I'm going to count cells J2 through J58. So we can see here, COUNTIF J2 through J58. Okay, those rows represent the females in this study. So the first 58 rows here of the data represent the females. Okay, the condition that I want to check is whether or not they were over. Okay, so that's what I'm going to keep track of in my simulation study, is whether or not they were over their daily recommended intake. This indicates that there were 25 women. Okay, so that COUNTIF statement there indicates that there are 25 women in which the vitamin A intake was over their daily recommended. On the other hand, for males, there were only 3. Now notice when I'm using the COUNTIF statement for the males in this data set are actually near the bottom, and the under-over measurement for the males are in cells J59 through J72. So that's what's being indicated here, are those cells. Okay, so let's go ahead and look at this data, in a table format here. So this right here in this particular cell, let's look at this value right here. Oops, let's go ahead and, sorry about that. Let's go ahead and look at this particular cell in the table. Again, this is for females, so it's in the first row here. For females, I had a total of 57 females. It's being specified right here. 57 total females in this study, 25 of which were over their intake of vitamin A. On the other hand, for males, there were only 14 males in this study, so a reduced number of males compared against the females. And 3 of those males were actually over their daily recommended intake of vitamin A. Visually, we can present a graph of that information on the right here. I just computed this graph in our spreadsheet. So there were a total of 57 females, 25 of which are over, and 32, I guess, were under. So the gray is the over box, and the darker gray is the under box here. Now, if females were getting about an appropriate amount of vitamin A, I would anticipate that about half of this box would be over and about half of this box would be under. In particular, for females, there's 57 total females in the study. Half of 57 is about 20, what is that, 28 and a half? So right around 28 or 29 females should be in each of these boxes if females are getting an appropriate amount of vitamin A. Okay, and that's again how I'm going to build my simulation model. On the other hand, for males, first of all, there's only 14 males, so it's a reduced number. Half of these should be over under in a situation where males are getting an appropriate amount of vitamin A. Now these numbers are slanted a little bit for the males. There's only 3 that are over and 11 that are under. Okay, so there's something very different going on here with the males than what we're seeing with the females. Let's go ahead and proceed with the schematics that we would use for this simulation or for this investigation. Let us first consider the analysis for males. The research question there, is there enough statistical evidence to say that WSU females are off target from their daily recommended intake for vitamin A? Okay, so we want to know whether or not they're off target or are they getting an appropriate amount. The research question here is asking, are these women here off target from what I would expect to get? Okay, and then the similar analysis for the males is simply, is there enough statistical evidence for WSU males from being off target from their daily recommended intake? As we've stated up above, this is going to be a 50-50 scenario again. So similar to the example that we just went through, similar to the helper-hinder example. The parameter value here is the probability or chance of being over on their intake of vitamin A. I'm going to build the simulation models under a situation of them being on target, and I'm going to need to determine whether or not 25 is an outlier against that situation. Likewise, for the males, I'm going to need to determine whether or not 3 is an outlier against that situation. So again, the approach here is to take the data that we have, set it aside for a moment, build a reference distribution for a particular situation. Here, that situation is going to be that they're on target for the amount of vitamin A intake, and then bring that 25 and that 3 back onto the picture to determine whether or not we're outliers against that situation. Okay, the purpose of the simulation, again, is to identify how much inherent variation is in that reference distribution. If there's not much inherent variation in these reference distributions, then it's going to be easier for a study outcome to be an outlier. On the other hand, if there's a whole lot of inherent variation, the dark gray pyramid here, then it's going to be more difficult for our study outcome to be an outlier against that situation. Now, if we just look at these two situations, the expected value for females is at 28.5. It's simply the 57. There were 57 females. And under a situation of being on target for their intake of vitamin A, it's going to be a 50-50 scenario. That's where that 28.5 is coming from. 25 is pretty close to that 28.5. I don't anticipate 25 being an outlier for the females. So if I had to guess, I'm going to say that females were taking in an appropriate amount of vitamin A. Or at least there's no evidence to suggest that they're not. On the other hand, for males should have been taking in about 7. Okay, so I should have had 7 males that were over and about 7 males that were under. There's only 14 males in this study. And I only saw 3 there, so 3 is somewhat, it's a little further away from, the expected than the up above. One thing that we should concern ourselves is when we're talking about whether or not we're an outlier, we have to be concerned about what the actual numbers are. Okay, so when I'm up around 28, 29, 25 doesn't seem very far off. Okay, it's what, 3.5 away? That isn't very far off from 28.5. On the other hand, for males, being 3 or 4 off is actually quite a bit on this number line. Okay, so we're talking about values of 7 versus 3 here. That's quite a bit on a number line that doesn't have very many observations on it. So when we're talking about 7, okay, having 3 is pretty substantially different. So being 4 away here might mean a lot on this number line, but being 4 away up here on this number line probably does not indicate that we're an outlier. We'll talk more about that in the sections coming up as well. All right, how about getting the p-values? For the females, okay, I just need to put in the observed outcome in the as extreme as box here, which is 25. So I had 25 overs for the females. So that's what number's going in here. And what the app is going to do is compute or determine the outcomes that were as extreme or more extreme than that. Okay, so it's going to add up the number of dots that are at 25, 24, 23, 22, all the way down to 0. So this number line actually goes all the way down to 0. And then it's going to look at the corresponding values of 32. Recall that the expected value here is 28.5. 28.5 subtract 25, and that's 3.5 away. So the corresponding upper value here is going to be 3.5 above 28.5. That's where the value of 32 is obtained from. So values as extreme or more extreme than 25 on the upper side are going to be values at 32, 33, 34, 35, all the way up. I guess this goes all the way up to 57, doesn't it? So it's going to add up all of those dots. We got to make sure and select the two-sided button when computing this p-value, but the app does that for us. And the p-value for this particular case is 0.419. This suggests that 25 is not an outlier at all in this distribution. In fact, there's over a 40% chance of seeing something as extreme or more extreme than our 25. On the other hand, for the males, so we have a similar situation or setup for the males. Probability of heads is at probability of success is at 50%. Sample size is at 14. I'm getting 1,000 repeated outcomes here. I'm placing 3, the study outcome, in the as extreme box down here. Again, selecting the two-sided. And we can see that for the males, the p-value is 0.0590, or about 6%. Okay, so that's suggesting that 3 is somewhat of an outlier against this reference distribution. It doesn't quite meet the 0.05 threshold, but it's certainly more of an outlier than what we saw for females. So let's go ahead and complete these analyses for both males and females. Let's go ahead and do the females first here. The research question again, is there enough evidence to say that WSU females are off target from their daily recommended intake for vitamin A? The p-value that we computed for this from up above was 0.419, which is 41.9%. Okay, be careful when looking at that. Some students actually get a little careless and say that's about 4%. Got to move that decimal 2 places to the right when computing a percentage, and not 1. That's about 41.9%. So the decision here is 0.419 less than 0.05. The answer to that is no, not even close, I guess. So our decision here is that we do not have enough evidence for the research question. Let's go ahead and write a conclusion. Call the three components. The first here is there is not enough evidence to say, that's the first component. We can get the research question, and the research question was that WSU females are off target from their daily recommended intake of vitamin A. So we do not have enough evidence in this situation to support that statement. And the p-value here is 0.419. So practically speaking, we do not have enough evidence to say that females are off target from their daily recommended intake. How about the analysis for males? The p-value from the males was at 0.059. So up here again, from their reference distribution, we have a computed p-value here of 0.059. Each of these were based on 1,000 repeated outcomes. Now, this is actually writing this as a percent, I guess, 5.9%. Is 0.059 less than 0.05? The answer to that is no. This time, it's pretty close. Okay, if we want to be real strict with our 0.05 threshold, we're going to end up saying that we do not have enough evidence. So there is not enough evidence for the research question. Again, if you allow me to take off my statistician hat for a minute, it is close though. So the p-value is real close to 0.05. So there may be some evidence, just not enough to confirm, or just not enough for what, statistical significance? Say it that way. So it doesn't meet that 0.05 threshold that we statisticians stick to, but it is close to that threshold. So the conclusion here is going to be much of the same as what we had for females if we stick to that very strict 0.05 threshold here. Just go ahead and copy and paste that over. Okay. There is not enough evidence to say that WSU males are off target from their daily recommended intake of vitamin A. The p-value, though, on this side is 0.059. Again, taking off the statistician hat, we can say that it was fairly close to 0.05, and therefore we might say there's marginal evidence. So let's go ahead and maybe make the following change to that. There is, what could we say, some evidence or marginal evidence. To say that WSU males are off target. Now, we talked about this in the previous section, that we statisticians aren't allowed to make statements like this because people will just end up having additional discussions by what do you mean by some evidence or what do you mean by marginal evidence. Okay, so as a practicing statistician, we don't make those types of statements. Okay, we really stick to our 0.05 threshold here. So I'm going to go ahead and take that statement that I just made and let's see here, let's do a strike through on that because we really don't allow ourselves to make those types of statements. Okay, let us consider the following three questions here to finish out this section. What is the scope of inference in this study? Well, the scope of inference in this study would be WSU students. We actually conducted our analysis on males and females separately. So in the female analysis, I guess, the scope of inference would be WSU females, and the male side of things, the scope of inference would be WSU males. But generally speaking, the scope of inference here is WSU students. Now, we shouldn't make conclusions about students at other schools unless we believe that the students at Winona State are like the students at the other schools. But strictly speaking, we don't have data from students from other schools, so we really shouldn't include these other schools in our scope of inference. How about the following question? Suppose that the p-value for the males was 2.8% instead of 5.9%. Does this change impact the scope of inference for the study? So no, does not have an impact on scope of inference. So our decision is different from our scope of inference. Scope of inference is whom we are trying to talk about. The scope of inference does not or is not influenced by what the study outcome actually arrives at. On the other hand, it does, changing the p-value as stated up above, does impact our decision. So this change to the p-value would change our decision. And hence, I guess, would change the conclusion as well. And hence would change the conclusion. How about the last question here? Let's consider the outcomes from this study for calcium instead of vitamin A. So here I'm looking at the calcium outcomes. Let's go ahead and move this on the next page so we can see it. There were still 57 females and 14 males. Okay, so those numbers didn't change. But for calcium intake, it looks like males, okay, if we look at males first, males were at 8. So 8 males were over their calcium intake, and 6 males were under their calcium intake. Well, that's pretty split on a 50-50 scenario. Okay, so just like what we did for the vitamin A analysis, if they're on target, I would expect about half of them to be over and about half of them to be under. And that's pretty close to a 50-50 scenario there for the males. On the other hand, for females, the expected number would again be about half of the 57, so right around 28, 29 females should be over, and around 28 or 29 females should be under. However, this data is suggesting that there aren't nearly as many females that are over the calcium intake as under. And in particular, many more females are under their level. So it's looking like for calcium that the males will be okay, but the females will probably be too low. I don't have a p-value that is being computed here, but I would anticipate that the females would actually be an outlier. So let's go ahead and write that up. So what do we want to say here? If students are on target for calcium, there should be about 50% over and 50% under. The expected count for males would be 7. Okay, so 7 over and 7 under. And the outcomes here, 8 and 6, are pretty close to the expected. On the other hand, for females, the outcomes (16) and 41 appear to be at least somewhat far away from 28.29 or 28.5, the expected outcome. So at least if I had to guess here, I would anticipate that the analysis for calcium is going to indicate that the p-value for females is really small, whereas the p-value for the males in calcium investigation is going to be somewhat high. Kind of the opposite effect that we saw for vitamin A. Okay, that's it for section 2.2. In the next section, we're actually going to start using our spreadsheet to compute these p-value quantities that we've been looking at through the reference distribution app. We're going to take we can actually get these p-value calculations through a spreadsheet, and that's what we'll do next. All right, thank you very much, and until next time.